Alright, I'm back with section 11.4, arc length parametrizations and curvature. There is just a lot of theorems to toss out at you here at the beginning and definitions. So the proofs for these are all in the textbook, so you can read for more details there, which I encourage you to do, as the textbook is quite readable. So please take advantage of that as well as you prepare for Wednesday's class. From chapter 9, we talked about parametric equations there and the arc length of the parametric curve, and that was all done with 2D parametrizations. This is the formula that we developed then, the Riemann sum. The limit as n goes to infinity of the sum from k equals 1 to n of the square root of that expression, and delta t was the difference in the endpoints of the interval divided by the number of subintervals, and t sub k is k times delta t. So that's how you got the next endpoint for each subinterval. And since that was the Riemann sum, we were able to say that the arc length could be computed by the definite integral that you see there. So this same idea works with vector valued functions for 3 dimensions, for 4 dimensions, as many dimensions as you would like. So here's the formal definition from your text. If C is a curve in R3, given by the vector function r of t equals x of t, y of t, z of t, for t in some interval from a to b, where x, y, and z are all differentiable functions of t, and the function is 1-to-1 from the interval AB to the curve C, then the length of the curve C from A to B is given by that expression. It's the L of AB, so the length from A to B, of the limit as n goes to infinity of the sum from k equals 1 to n of the magnitude of that vector difference. Remember, those vectors will point, if we consider them position vectors, they will point to an endpoint which is located on the curve, and so we're finding the magnitude of the vector that goes between those two endpoints. And as n goes to infinity, the number of, how we say, difference vectors, r of t sub k minus r of t sub k minus 1, also goes to infinity, and their individual lengths go towards 0. And so the more they go towards 0, the better that sum is of an approximation of the actual arc length. As you can see there, we've got several points plotted out on the curve. The basic idea is that we move those points closer and closer and closer together so that there is no space in between them, and then the line segments connecting those points basically become the curve itself, and that's how you can get the arc length of the vector valued function that represents a given space curve. Okay, well, just like we could turn the Riemann sum in chapter 9 into a definite integral, we're going to do the same thing here. So this is the example for a curve in R3 with all the same suppositions that we had on the previous slides. And we get that the length of the curve C from R of A to R of B is given by the definite integral there. It's the integral from A to B of the magnitude of R prime of t dt. And remember, how you find that magnitude is by taking the square root of x prime of t squared plus y prime of t squared plus z prime of t squared. And so that's very similar to the definite integral we had here. This was just the 2-dimensional analog of what we're now doing with 3 dimensions. So it's just we're adding on that third component, x prime of t squared. But it's the same idea for the arc length of a space curve. Alright, we're going to talk about different parametrizations. A given vector curve has infinitely many different parametrizations. We've looked at ways to do that with, say, the unit circle. You could parameterize it by cosine t sine t. You could parameterize it by sine t cosine t. You could also parameterize it by cosine kt comma sine kt. And as long as those k values are the same thing, we would have different rates and directions of tracing, but they would all produce the same unit circle. So if C is a graph of a differentiable vector function r of t defined on an interval I, then the function r of t is said to be an arc length parameterization for C if this is true. So if the definite integral from C to D of the magnitude of r prime of t dt is simply d minus c for all c's and d's in that interval, then it's a particular type of parametrization. It's called an arc length parameterization. Remember, there are multiple types of parameterization. There are an infinite number of parameterizations for a given space curve. But if this is true, then the parameterization that we're looking at is known as an arc length parameterization. So some facts about that. When a curve is parameterized by arc length, the length of every segment of the curve is equal to the change in value of the parameter. So here's a couple examples, one that is and one is not. If you look at r sub 1 here, cosine t sine t, versus r sub 2, cosine 3t and sine 3t, both of those produce the unit circle, but only the first is an arc length parameterization. And you can verify that by, if you integrate r prime, let's say r sub 1 prime of t, and take its magnitude between any two values, let's say you do from 0 to 2 pi, then the value of the arc length of r sub 1 of t over 0 to 2 pi is exactly 2 pi. That is not the case with r sub 2 of t. If you take the derivatives of both components, square them, add them together, take the square root, and integrate from 0 to 2 pi, you do not get 2 pi minus 0 or 2 pi. You get something different. I'm going to leave it to you to do the math, and you can verify that. But the reason why r sub 1 is an arc length parameterization and r sub 2 is not is that r sub 1, if you integrate the arc length if you integrate the magnitude of the derivative of r sub 1 of t from c to d, the answer will be d minus c. That is not the case with r sub 2. Alright, further with arc length parameterizations, we still got a curve in 3 space such that r of t is 1 to 1 on the interval ab, and there's a non-zero derivative. If you define the real valued function s of t by that definite integral, notice that's the integral from a to t of the magnitude of r prime of tau d tau, then dr ds, so if we take the derivative of r with respect to s, it is t of t. That's the unit tangent vector function. Unit tangent vector we talked about in 11.3. A few more facts here about arc length parameterizations. With most parameterizations of a curve, both the direction and the magnitude of the tangent vectors change as the particle travels along the curve. But when you do a curve that is parameterized by arc length, only the direction changes because the derivative will always be a unit vector in that case. Another new term, curvature. So if C is the graph of a vector function r of s defined on an interval I, parameterized by arc length s, and with unit tangent vector t, that's what we're looking at. So notice instead of r of t, we're going with r of s. So when s is used in your text, it's standing for the arc length parameter. So we know it's an arc length parameterization. Well, we're going to define the curvature kappa of C at a point on the curve to be the scalar given here. Kappa is the magnitude of dt ds. So it's the magnitude of the rate of change of the unit tangent vector with respect to the arc length parameter. How fast is the unit tangent vector changing with respect to arc length? That's what we're defining as curvature. So notice again that it's a scalar. So you might get curvature of 2, for instance. If the unit tangent vector t has a non-zero derivative, then it will be true that the derivative of the unit tangent vector with respect to the arc length parameter s is equal to the curvature kappa times the unit normal vector. I'm just throwing a lot of definitions and theorems at you. Again, these are more fully explained in the text, so if you take some time to read through that before Wednesday's class, that would definitely be helpful. There are multiple ways to calculate curvature. So this is true, but this is not very easy to work with. So here are a couple ways to calculate curvature. The curvature kappa of C at a point on the curve is given by here. It's the magnitude of the unit tangent vector, the derivative of the unit tangent vector, divided by the magnitude of r prime. Or kappa can be found by taking the cross product of r prime and r double prime, the magnitude of that, and dividing by the magnitude of r prime of t cubed. Again, presenting these without proof, examine the text for the reasoning behind why these are the case. Here's another one. If y equals f of x is a twice differentiable function, then the curvature of the graph of f is given here. So this is something that you can do in 2D when you have y equals f of x. So you don't have a vector valued function, you have a real valued function. You can find the curvature kappa by applying that formula or by applying this formula. So x prime of t, y double prime of t minus x double prime of t times y prime of t. So you have to be able to take multiple derivatives, but this is another formula for curvature. So depending on the type of function you have, you may want to use this formula for curvature, or this formula, or one of these two. So for vector valued functions, this one obviously seems to make more sense. But if you have y equals f of x, you probably want to use one of these two formulas. And I think I'm going to stop there. We'll pick up with talking about radius of curvature in class on Wednesday. I think that's enough for this video. You can try out obviously some problems in WebAssign to see if you can calculate curvature 11.4 or if you can calculate arc length. Those are the kind of the two examples or the definitions and theorems that we've given you so far. But you can use those to try out some of the problems in 11.4. And I will see you on Wednesday. Well,